Alright, so first we want to start with determining if each function represents growth or decay model and then writing the rate of change. If you remember in class, if it's growing, it's going to be greater than 1. If it's decaying, it's going to be less than 1. So let's look at each example. Here, if we're looking at our starting amount, 1.23, this is greater than 1, so it would be growth, and the rate of change would be 23%. So you take it's the number that is bigger than 1. Then if you look at number 2, we have decay because 0.88 is less than 1. So this would be decay. If we subtracted 0.88 from 1, that would leave us with 12%, and so that's how much it decays. Let's try number 3. Number 3, it is bigger than 1, so that would be growth. And if we subtracted 1 from this, we'd be left with 9, or 0.09, so in percent, that would be 9%. So we're looking at the difference from 1. So the difference from 1 here was 23, so that would be 23%. The difference from 1 here would be 12, so that's 12%, and the difference from 1 here is 9. I'm going to leave 4 through 6 for you to try. Now, let's look at 7. 7 says, with only about 8,000 bowhead whales remaining, their species may soon become extinct. Their population decreases each year by 12. What will be the estimated population of these whales in 3 years? So we want to look at our starting amount. Our starting amount, we started with 8,000, so that's what we would want to write here. Then we want to know the growth or decay factor. Since it's going to become distinct and it uses decreases, that means it's going to have a decay factor, and the decay factor is 12%. So remember, to get this we have to do 1 minus 0.12. So our decay factor would be 0.88. Then we look at the time period. So we want to estimate the population of these whales in 3 years. So our time is 3. If you remember from the beginning, our formula for this is y equals a times b raised to the x. So we're just going to plug this in. A is our starting amount. So we'd plug in 8,000 for A. B is our growth or decay factor, so we'd plug in 0.88. And it's raised to the x, which is the time period. So if you plug 8,000 times 0.88 raised to the third in your calculator, you should get 5,451.8 wells. I would take 5,451 wells because you can't have 0.8 of a well. Sorry about that. Let's look at number 8. So it says the population of Chelsea is 20,000 and has grown by 8% each year. What will the population be in 10 years? So if the population of Chelsea is 20,000 right now, that's what we would want to write down is 20,000. That's our A. Then we would want to write down how much it grows or decays. Since it says it grows, that would be growth, and that's our B. So by 8%, so if it's growing, we have to add this decimal. So this decimal would actually be 0.08. So we would add 0.08 to 1. So we would get 1.08, and that's what we would write right here. And then we want to plug in our time period. So it says, what will the population be in 10 years? So the time period is 10, and that's x. So if we plug it into y equals a times b raised to the x, that gives us y times 20,000, or y equals 20,000 times 1.08 raised to the 10th. If you plug that in your calculator, you would get 43,178.5 people, but we can't have half of a person, so I'd take 43,178 people. Okay, I wanted to go over this one again because it uses depreciates, and I want to make sure we know what depreciate means. In class we talked about it, and it means decrease. So here we know we're going to have a decay factor since it's decreasing. So a laptop that cost $1,800 depreciates at the rate of 3% per year. What will the value of the laptop be in 7 years? So our starting amount would be $1,800. It decreases at a rate of 3%, so we would have to do 1 minus 0.03, and that would give us 0.97. And we want to know what the value of the laptop will be in 7 years. So our time would be 7. So if we plug this in, that would give us y equals our starting amount, which is 1,800, times our decay, which is 0.97, raised to the 7th. If you plug that into your calculator, you should get $1,454.37. Flipping the page, we're going to look at number 12. So number 12 says, Alex invests $2,500 into an account with an annual interest rate of 6% compounded yearly. What is his account balance after 4 years? Okay, remember, principal, or P, stands for principal, which is our starting amount. Alex invested $2,500 at the beginning. Then he had an interest rate of 6%. So he's gaining interest, so we would need to add 1 to 0.06, which would give us 1.06. So that would be our rate of change. And then we want to know how much he would have after 4 years, and so that's our time. So if we plug that in, it would be the same as this is A, this is B, and this is X. So we could do 2,500 times 1.06 raised to the 4th. So if you plug that in your calculator, you should get $3,156.19. Okay, I'm going to leave 13 for you, and then we're going to look at number 14. So, number 14 says, for each function below, identify the starting amount, whether the function represents exponential growth or decay, and the growth-decay factor. Alright, so our starting amount, if we look at our generic equation, it's y equals a times b to the x, where a is our starting amount. So in number 14, our starting amount would be 5. If you don't know whether 1/3 is greater than 1 or less than 1, so you can tell whether it's growth or decay, divide it in your calculator. If you divide 1 by 3, you realize that it is smaller than 1, and so therefore this would be decay. And then its growth or decay factor is just b. So remember that this is b, this is a. So our growth or decay factor would simply be 1/3. Okay? So let's try 15 now that we know. Our starting amount is always a, so our starting amount here is 8. Is 5 bigger than 1? Yep. So that would be a growth factor. And then our growth factor is simply our b, which is 5. So I think you guys can probably do 16 now. Okay, so let's talk through 17. 17 says the number of bacteria on a telephone grows throughout the day. Suppose there are 250 bacteria on your phone right now, and they reproduce by a factor of 8 every minute. Write an equation that describes the number of bacteria B on the phone after n hours. So we want to know how many bacteria there will be after n hours. So we know it's going to be Bn equals something, okay? So we want to look at our starting amount. So if we look up here, it says there are 250 bacteria on your phone right now. So our starting amount is 250. So which one of these has 250 first? C. That's the only one that has 250 first. Then it grows by 8. So isn't it A times B to the X? A times B to the X. So our A was 250. Our B is 8. So 250 times 8. C is the only answer that makes sense. Let's look at another one like that. Number 18 says the population of dolphins in the Atlantic Ocean increases by a factor of 2 every year. Currently, there are 75,000 dolphins. Write an equation that describes the number of dolphins D in the Atlantic Ocean after Y years. So again, we're looking at how many dolphins there are. So it will be our starting amount times the change raised to the time. So our starting amount here, it says currently there are 75,000 dolphins. So we know it's going to be dy equals 75,000. And then our b is what it changes by, so it says it increases by a factor of 2 every year. So that would be times 2, and then our time is y years. So it would be raised to the y. So which one matches this? It's also C here as well. Okay. I'm going to let you attempt 19. And let's look at 20. So number 20, we did some of these yesterday, and they're pretty simple. If we want to match the graph with this function, then we want to kind of create an x and y table where we can plug some things in for x and figure out what y will equal. So let's just say we start with 0. If I plug in 0 here, then that anything raised to the 0 power is 1. So what I want to look is say which one of these has 0, 1 plotted. So 0, 1, not this one because that's here. So it can't be that one. This one has it. 0, 1. This one does not have it. And this one also has it. So now we have to do a second one. So if I want to plug in, let's say we do 1 now for x. So if I plug in 1 for x, then that just raises it, that just makes it the same. So it's 1/4. If you put in your calculator 1/4, it's going to give you 0.25. So from here, I want to see where 1 and 0.25 is plotted. So here, if I went to 1, 0.25 would be somewhere right here. So it can't be this one. So here, if I went 1.25, that lands on the graph. So it would have to be D. Okay. Let's also look at 21 just to make sure we got it. So here, again, we want to make our x and y table so we can plug in something in for x. So I start with 0 because I know that anything raised to the 0 power is 1. So I'm looking for 0, 1. So 0, 1 is here. That one works. 0, 1 again is here, so this one does not work. C also works, it's at 0, 1, but D is not at 0, 1. So I know that it can't be B and it can't be D, so I need to plug in something else. So let's try 1 in for x. So if I did 2 to the first, that's just going to give me 2. So I'm looking for 1, 2. So if I go over to the right, up 2, this one doesn't actually land on this line, so it can't be A. Let's check this one. This one works, so this would be C. Okay. 22 and 23, I want to make sure that you know how to do this because this will be on the test and we haven't talked about it much. They want to know whether the graphs here are increasing or decreasing, whether it has growth or decay, the domain, and the range. Okay, so it's been a while since we've talked about domain. Remember that domain is our x values and range is our y value. Okay? We know that something is increasing if it starts at the bottom and works its way up. So looking from left to right, this starts and it goes up like on a roller coaster. You start at the bottom and then you kind of creep your way up. So this one would actually be increasing. Okay? So if it's increasing, that means that it's going to be growing. That should make sense, because if you increase calories, you're going to grow bigger, right? Or if you increase your weight you're lifting, you're going to get more muscle. Alright, so if we're talking about our x, just because this graph stops right here does not mean that it doesn't keep going. Our domain is always going to be all real numbers, because this is always going to get as close as it can here and keep going, and this is always going to be going up forever, so it's going to touch every x value all the way across. Okay? And then our y value is how low or how high it is. So our bottom right here is on the y-axis, and then it keeps going up forever. So its lowest point is at 0. So y has to be greater than 0. Okay. I know that's new, so let's try number 23 as well. So here, if we start left from right, if we think of this as a roller coaster, we'd be coming down the hill. And so since we're coming down, that's going to be decreasing. And if it's decreasing, that also means that it's decaying. Okay? Because if population's decreasing, then it's getting smaller, which is what decay means. Alright, our domain is our x, and we know that the domain is always all real numbers. Okay? You can put that little sign, or you can put ARN, whichever one you like better. Okay? And then our range. So we want to look at its highest point and its lowest point. Its highest point, we don't know where it came from, but we do know its lowest point. So its lowest point right here, if we count down, that's at -2. And so that means that y would have to be greater than -2. So something I want to explain, wherever it looks like its lowest is, whatever that is on the y-axis right here, it's -2, it can never actually touch this point right here. It's always going to be greater. So here, when it was at, it looked like its lowest point was at 0, it can't actually touch 0, but it gets as close as it can, and then goes up forever. So wherever it looks like it's last intersecting, whether it's -2 or 0, y is always greater than that. Okay? Let's look at 24 and 25. Okay, so they want us to graph each function. In order to do this, we're going to have to pick points to go in for x, which they actually already gave to us. We're going to just plug those in each time. So let's start with -2 and plug it in. So that would give me y equals 2 times 3 to the -2. Okay? Remember, this -2 only affects what is right in front of it, so it only affects this 3. So when we go to change it to positive and we have to move it down, if we put this over 1 and we had to move this down, we would get 2 over 3 squared. And I know that 3 squared is 9, so that would give me 2 over 9, and if you plug that in your calculator, that ends up being 0.2. Okay? So now let's plug in -1 for x. So that would give me y equals 2 times 3 to the -1. Again, the negative only affects the 3. So when we put this over 1 and we decide to move this down, we're only moving 3. So that gives me 2 over 3 to the first. 3 to the first is just 3. So 2 over 3. If you plug that in your calculator, it's going to give you 0.7. Okay? What is anything raised to the 0 power? It's 1. So if we plug 0 in here, we get 2 times 3 to the 0. And remember, it's the same thing again. This exponent only applies to the 3. So I'm going to bring my 2 out. 3 to the 0 is 1, and I know 2 times 1 is 2. So we'd write 2 by 0. Okay, and then we plug in 1, so we get y equals 2 times 3 to the first. 3 to the first is just 3, and 2 times 3 is 6. So we'd write 6 here, and then we're going to plug in 2 for x. So that gives us y equals 2 times 3 squared. I know that 3 squared is 9, so I get 2 times 9, and you can actually just plug this whole thing in your calculator, and that's going to give you 18. Okay, so let's go ahead and plot our points. So if we're plotting -2 and 0.2, we want to go to -2 on the x-axis, so I go left 2, and then I go up just a tiny smidge and put a dot. Then I would plot -1 and 0.7, so I'd go left 1 and go up a little bit higher on that one, but not quite at 1 because it's smaller than 1. Then I would plot 0, 2, so I wouldn't go anywhere on the x-axis, but I'd go up 2 and put a dot. Then we plot 1, 6, so we go to the right one, up 1, 2, 3, 4, 5, 6. And then lastly, we would plot 2, 18. And I don't actually have an 18, so I'm going to put it about right here. And so when I plot this, I just want to connect all my dots. And you can even continue this out if you want. And up. Okay? So it kind of makes that hook shape. All of your exponential graphs should make the hook shape, either this way. Sometimes, as we saw yesterday, it can go down. Okay? So let's look at 25 as well. So starting with 25, we want to plug in -2. So let's do y equals 1/4 raised to the -2. Now remember, to get rid of this negative, since it's already in a fraction, we just flip that fraction. So it would end up being 4/1 squared. So I know 1 squared is just 1, 4 squared is 16. So I can plug in 16 here, because 16/1 is just 16. Next, I'm going to plug in a -1. So I'm going to do y equals 1/4 to the -1. All we have to do to get rid of that negative is to flip it. And I know that 4/1 to the first is just 4. So I'm going to plug in 4. Here we have 1/4 raised to the 0. There's nothing outside, so that is simply going to be 1. Then we want to raise it to the first. Anything raised to the first is itself. So 1/4 here is just 1/4. If you put that in your calculator, that's going to be 0.25. And then raising it to the second. let's write that one out. So we're going to do y equals 1 over 4 raised to the second. That's the same thing as, you can either do 0.25 squared, or you can say 1 squared over 4 squared. Either way you want to do it is fine. This would give me 1 over 16, and then I would have to divide, and then if you plug this in, this would give you 0.06. So I'm going to come over here and put 0.06. So now we're going to graph it. So -2, 16, -2, and this doesn't actually go up to 16, but I'm going to put it about right here. Then -1, 4. I'm going to go to the left one, up 1, 2, 3, 4, and put a dot. Then we're going to plot 0, 1, so I don't go right or left at all, but I'm going to go up 1 and put a dot. And then for 25, we're going to go to the right one. We're going 0.25, so it's very close to 0, but not quite there. And then 0.06 is going to be even closer, so I'm going to put it really close. And then all I have to do is connect all of these so that it makes my hook. And if you want to extend this out, you can. And there's our graph. So you should have a few more minutes in class to be working on some of these. If you do not understand how to work a couple of them, please be sure to come see me tomorrow morning before school, and I'll be happy to work through any of them that you need help with. But for now, I would like you to try to work a few on your own.